This is project 1, video number 2, the one in which we actually code up the program. And start up MATLAB, type edit. I'm going to call this function. And I'm returning an array, so I'll put open bracket. For the first element of the array is going to be E, the magnitude, and the second one, theta, the angle at which E is directed, and that return variable, that return array, is equal to my function name, get E, maybe call it get E field. Hopefully you'll be able to think of a name that's just as good but different. And let's suppose be a function of Q, the charge of each of those 101 particles. I think I got 100 particles in the last video, but it's actually 101. We got an and for the function, and then we get to work. So for my code outline that I generated before, we got to initialize a couple of things, y and k. So y equals 1 meters, k equals 8.99 E9 Newton meter squared per coulomb squared. Then what? We got the X array is equal to lin space. I want to make sure that that's the way that actually works. I think I'll go with test equals lin space 0, 10, and say I want 11 values. I think it's 11 values, but if it's spaces, yeah, okay, that was perfect. So that last argument for lin space is the number of values that you want. So had I done that, well, so we're going 0 to 1, and we want 101 values, so they should be spaced out at hundredths. And sure enough, it goes 0.99 to 1 at the very end there. Okay, so it was just a quick little test. And I wanted to say X array equals lin space 0 to 1 and 101 steps. I tested that, so I don't think I'm going to print that out. Then their R array is equal to the square root of X array. So yeah, I'm wondering if maybe I should start out with a smaller number. And now let's see what it looks like. I go R array. I might want to change that to a smaller number for testing purposes, and then change back. That's what I was thinking about. R array is equal to square root of X array dot to the power of 2. The dot meaning do it element by element rather than trying to square the whole array as an entity, as a matrix. And then plus the y squared. Y is just a single value, so I don't need to mess around with a dot on that. So we'll see if that works. Then my thinking was that gives the array of R values. The gamma array, so that's that upper angle, is the arctangent of the X array. I think I want to work strictly in degrees. I feel like working in degrees. I choose to work in degrees. So I think what I got to do is stick a D on the end of that. Let's play around with that a little bit. A tan D. If I got a 1, 2 square root of 3 triangle, 1 over the square root of 3. Should give me 30 degrees. Okay, so that's cool. A tan D seems to be the arctangent in degrees command. And so gamma array is equal to A tan D of, I think it's y over x. No, it was x over y. That's why I worked with that angle. So it would be x array over y. I chose that angle so I wouldn't run into the 0 on the bottom issue. 0 in the denominator, divide by 0 situation. So let's see if I, x array over y, over the y value. Okay, so that gives me that, and then the theta array. So that's a different variable name than just the theta that I'm going to for my final answer for the actual direction of the total electric field. But the theta array, I think it is just the gamma array plus 90 degrees. Let's check, see if I remember that right. Theta array is the gamma array. Okay, and then if the charge is negative, we add an extra 180 degrees to every element of the theta array. So if I'm not sure I remember how that if then else goes. I'm going to go if Q less than 0, then what we do is theta array equals theta array plus 180 to reverse the direction of to take into account that the electric field is in the opposite direction to the direction from the charged particle to the point in question. Alright. So then what? Calculate the E array. Very cool. The electric field array is equal to K times Q. Q is going to be given as an argument, divided by, I think I'm going to go dot slash R array dot to the power of 2. So I do the R array dot to the power 2. That gives me an array that's every element is squared, is the square of what was in the R array. And then I'm dividing this pure number by element the R array squared, that new array that I just got, on an element by element basis. So I think that'll do the trick. Back to the plan, and it says get the x component of each element of that array, store it in an array. Ex array is equal to E array dot star cosine of theta array. So theta array is 101 values. When I took the cosine of that, I get 101 values, and I want to do this multiplication on an element by element basis. So that's why I use the dot star instead of just the star. I'm going to copy and paste this because EY array is almost the same thing, except we need a sign there. And I want to work in degrees, and that's the sine D and the cosine D. See if I've, yeah, okay, I got D everywhere. There's a trig function or an inverse trig function so far. So I'm working in degrees. And then EX is the sum of that. I want to play around with that. I go, what was my test? Does that still exist? And now it's 100 of them. So, test. I think I can just do that. So test just has 10 elements. If I do sum of test, I think that just adds up all the elements, which should give me 19, 27, 34, 45, 49, 52, 54, 55. Okay, so that's how you add up all the elements in an array. So EX, the total, is equal to sum of EX array and EY is the sum of EY array. And sum of all the elements in the EY array. I think I should hit a save. So save that as getfield.m, and I'm going to go ahead and click on the save button. It looks like I got it. Saved. Should have saved earlier. But I guess nothing crashed, so I lucked out. So I got the EY, and then the total E is the square root of the sum of the squares of the components. So E equals square root those are just numbers at this point, so I don't have to worry about that dot. And then I want to play around with that atan a little bit, atan 2, and make sure I get the right idea on that. So if I got a vector in the first quadrant, let's say I'm at 1, 1, I would expect atan 2 to give me 45 degrees. That's not a 45. Let's try, see if there's an atan 2D. So that's not any good. I think help on atan 2. See also Okay, let's try a tan D2. Okay, no such thing. So I'm going to get the tangent. Looks like all I can use is a tan 2. And presumably that gives me the angle I'm looking for in radians. So I'll multiply times pi divided by, times 180 divided by pi to convert that to degrees. Alright, so that's working. That's 45 degrees. Now, if maybe I should, just use this as a little scratch pad. If I'm over there, I should get 45 degrees. So 45 degrees. If I'm over here, I should get 90 plus 45, so that would be 135 degrees. If this point is minus 1, 1. And let's go ahead and see if that works. It did not. So a tan 2 at minus 1, 1 gives me a minus 45 degrees. So I think I better take a better look at the documentation on that. Help. A tan 2 seemed to be working for me, and yeah, the 4-quadrant inverse tangent, but the argument order is y comma x. Okay, so the first one worked because they were both the same. This one, if I want to be checking out the point minus 1, 1, the arguments have to be 1, minus 1. So I'll remember the y component goes first. Good thing I played around with this a little bit. So let's try that. I want, this is actually it. I paused the video and played around with it a little bit. But there's y is equal to, so this is minus 1, 1, x is equal to minus 1, y is equal to 1, and I get the 135 degrees. Now, if, so this one worked, but it was 1, 1, so it didn't tell me about the mistake I was making. If I'm down here, this should be 225. Or equivalently, the same angle, or same position, can be, or the same angle can be written as minus, it's 90 plus 45, so minus 135 degrees. So either of those angles, the 180 plus 45 is 225, or minus 135, I hope I said 225 degrees, or minus 135 degrees. Just a quick check, 10. These should add up. If I take the positive of that, they should add up to 360. So it'd be 130 and 220 would be 350, and then 5 and 5, another 10 gives me. Okay. So this is the position minus 1, minus 1, and if I do that one, I want to do them all since I got messed up there. But I should get either 225 or minus 135. Minus 135. Cool. And then the last one, and I got to remember to put it in the right order. It goes y comma x for the arguments there. The last one would be right over here. I see that coming out negative, so I'll just work with the negative here. It's minus 45 degrees if I'm at 1 comma minus 1. And I got to type that in as a tan 2 of minus 1 comma 1. Minus 1 comma 1. That's minus 45 degrees. Okay, so this is working. So the two things I had to worry about, there is no a tan 2 for degrees, so I gotta just use the regular a tan 2, which gives it to me in radians, and convert that to degrees. And I gotta remember that it goes y comma x. Okay, I think I'm in business. So technically I had it wrong in here. These two have to be interchanged. So EX and EY have to be interchanged with each other. So I'm going to swap. And you should erase it and fix it when you're doing yours. Alright. And so I think I'm in a position to type in calculation for theta is equal to a tan 2 of e y comma e x, and then times 180 slash pi. And then those are the two return variables, and that should actually do it for this function. Just hit delete there to shorten it by one line. So let's try saving it. Get E field. And running it. Get E field. And then I'll do it with that 2 times 10 to the minus 5th that they asked us to evaluate it at, or I was required to evaluate it at as part of the project under the pencil and paper part. So let's see if we get an error. It didn't like, oh my goodness, I apparently have an extra underscore in there. Don't remember typing that. Save. Run. Alright, so it calculated something. Gave us back just one of the values. I think if you go, like, you could use any variables here, but I'll use e theta because they make sense to me. Equals get E field of 2e times 10 to the minus 5th. We get both of them, so all it gave was the first one. So it's claiming 112 degrees. I guess I'm kind of curious to see if that makes sense right off the bat. So we got a bunch of positive charged particles lined up along here. They're all going to be creating something that's partly leftward and partly upward. So yeah, 100 and some odd degrees, between 90 and 180 makes sense to me. So it was saying 112 degrees, so that's a sensible answer for the angle. For the magnitude, let's take off a little bit of stuff. One of these semicolons. Alright, the EX array. Let's look at the last element in the EX array. Hopefully we can do that. 101 all by itself. It says it's -6, but I got a feeling that we got a times 10 to the something. So let's look at the start of this. Times 10 to the 4th. So -6 times 10 to the 4th. And when I did it, that number does not seem familiar. I got 8 times 10 to the 4th. Oh, for E, the X was X component. Is that what I'm looking at? Yeah. The X component. And what do we get? Oh, minus. Good. 6.3569 times 10 to the 4th. And I had minus 6.357 times 10 to the 4th. So very close. Oh, 69. Okay. So yeah, that's cool. I thought it was so this rounds to 4 sig figs to minus 6.357 times 10 to the 4th. Minus 6.357 times 10 to the 4th. Alright. So that one seems to be working. Let's make sure this one's good as well. I mean, if I left off a D or something, for instance, I would be checking that. So I'll save that. Run it. And this time I got a positive 0.6357. Looks like it's different by a factor of 10. But this time, the way it's displayed is times 10 to the 5th. Okay, so 0.6. Oh, look at that. That's exact. You know, the way I rounded it, that's the exact same thing. 0.6357 times 10 to the 5th. And that's what I've got. If I slide the decimal place all the way over here, it's 1, 2, 3, 4, 5 places. 0.6357 times 10 to the 5th. Alright, so the things that we're able to check make sense. Well, able to check rather easily, especially because they required that to be in the pencil and paper part of the solution. They're making sense. Let's before I get started on the documentation video, make sure we're not printing out stuff that we're not supposed to. So it returns the array, it gives the return variable and nothing else. And indeed, if you run it without this part, it just returns the first element of that array. So the angle makes sense. The intermediate calculations agree. Let's call that a wrap for project 1 video number 2, the one where we actually code it up, and then I'll save the documentation for video 3 as usual.